This video will demonstrate the modeling of a double pendulum using the Multibody Dynamics module, available for use with the Structural Mechanics module. The primary aim of this model is to perform a flexible multibody analysis. Here we demonstrate various features available in the Multibody Dynamics module to model joints between mechanical components, such as joint forces and motion tracking. We will perform a transient analysis of the double pendulum motion and track the locus of the bottom tip of the double pendulum as it oscillates under gravity load. To start building the model, click the Model Wizard button. Choose a 3D spatial dimension and then select Multibody Dynamics from the Structural Mechanics branch and add it. Then click the Study button and choose the time-dependent option in the Select Study window. Click on the Done button and begin setting up the model. We start by importing the geometry sequence from an existing Comsol file. In the Geometry tab, click on the Insert Sequence button and follow the path of the existing file from which we intend to import the geometry sequence. It's important to note that the two components are in contact, so choose the Form and Assembly option. Click Build All to create the required geometry. Create selections of boundaries on the hinge pin and the barrel hinge to help with the joint definition later on in the modeling process. In the Definitions tab, click the Explicit button. To better visualize the hinge pin boundaries, we will hide the barrel hinge in the Graphics window. Click the Select and Hide button in the Graphics window and select the barrel hinge. Choose Boundary as the geometric entity level and select one of the boundaries on the pin surface. And then, check the Group by Continuous Tangent option in the Selection Settings window. This will select all the pin outer boundaries. Unhide the barrel hinge and repeat the selection creation process for the inner boundaries of the barrel hinge. We repeat this process on the barrel hinge to select all the interior boundaries, which will form the part of the joint with the hinge pin. Perform the same boundary selection process to create a group of boundaries around which the pendulum will rotate. We now choose aluminum as the material for both the components of the pendulum. In the Home tab, click the Add Material button. From the built-in library, select Aluminum and choose Add to Component. Then close the window. The default material model is the linear elastic material. We will retain the default settings for the material as we intend to perform a flexible multibody analysis. Next, we choose groups of boundaries which will form the joint between the pendulum arms. In the Physics tab, click Boundaries and select Attachment. In the Settings window, from the Selection drop-down menu, choose Explicit 1. This corresponds to the attachment for the boundaries corresponding to the hinge pin. Create another attachment corresponding to the boundaries of the barrel hinge by clicking Boundaries in the Physics tab, choosing Attachment, and selecting Explicit 2 from the Selection drop-down menu. Under Attachment 2, a joint between these two attachments can now be created. In the ribbon, click the Global button and select a hinge joint. In the Joint Setting window, you can view the joint sketch by expanding the Sketch section. Choose Attachment 1 as the source, and Attachment 2 as the destination attachments for the joint. We retain the default centroid as source as the center of the joint, and specify the joint axis to be along the y-axis. Choose a rigid connector boundary condition, and impose it on the inner boundaries of the component with the hinge pin. This imposes a prescribed rotation, as well as displacement about an arbitrary point, selected as center of rotation. Constrain displacements in all directions, and rotation in the x and z directions, thus allowing only rotation in the y direction. Add a gravity node to account for the weight of both components. We will keep the default mesh settings for this model, so we will go to the Home tab and click Build Mesh to build the mesh. In the Time Dependent node, in the Times Edit field, change the settings such that we solve for 20 seconds, with an interval of 0.025 seconds. In the ribbon, click the Compute button. Required analysis will now be performed on the solved model. The default plots created are for the displacement and the component velocity. Quantities can also be viewed at different instances in time. In the current model, we will plot the joint forces and the bottom tip displacement with respect to time. In the Home tab, click the Add Plot Group button and select 1D plot group. Then add a global plot. In the Plot Settings menu, click Replace Expression and go to Multibody Dynamics, Hinge Joints, Hinge Joint 1, Joint Force, and choose the X component. You can now copy this expression and paste it in the fields below, replacing the suffix X with the Y and Z respectively to plot the Y and Z components. To plot the tip trajectory, create another 1D plot group and choose a point plot. Add any point on the bottom face to the selection, and in the expression field, type Z, the Z coordinate of the tip. In the edit field, for the x-axis of this plot, type X to choose the X coordinate of the tip. Click the plot button to view the bottom tip trajectory. Finally, click the player button to view an animation showing the bottom tip displacement over the 20-second interval. Learn more about this and similar models in our model gallery.